In this video, we're going to look at electric field and basically how do charged objects know that they should experience a force based on other charged objects. And so electric field is the way that charges communicate to one another over a distance. Because they create this field around them, it can then exert forces on other charges. So in order to measure electric field, or in order to denote a direction or convention for electric field, we will consider a test charge. And so test charges are always positive, and so the direction that a test charge would go, that's what we say the direction of the electric field is directed. And so if we were to put a charge right here and we just have some positive charge here, and if we ask ourselves what would this positive charge do, it would be repelled from the positive charge over here. It would be attracted to this negative charge and attracted to this negative charge. So we say that the force is in this direction because the field, the electric field, is also in that direction. We can quantify this electric field by using the equation of F over Q naught, meaning, well, what's the force that our test charge is experiencing? And if we divide it by the amount of charge that it has, it gives us this 2 newtons per coulomb. So in this situation, we have a 3 times 10 to the negative 8th coulombs that's experiencing this 6 times 10 to the negative 8th newtons. And if we look at this ratio of force per coulomb, that gives us this idea of the amount or the strength of the field that it is sitting in. And so we can use that to predict, well, what if we had a charge of 12 times 10 to the 8th coulombs? What do you think the force would be? Well, using that 2 newtons per coulombs, we can see that it would be 24 times 10 to the negative 8th. This gives us this idea of an electric field and the strength of an electric field. So we get the electric field by taking the force that a test charge would experience divided by the test charge itself. Now, knowing what we know about Coulomb's law, we can simplify this, and we'll do that in a moment. But one thing to notice here, the units are newtons per coulomb. So based on the electric field, we can find the force that a charge would feel if it were in the presence of that field. So given that this situation here in A and B, we have 2 newtons per coulomb electric field that is experienced at both of these points here. And so we want to know what's the force that this experiences in each situation. Well, we can find the force by taking the test charge times the electric field. And this gives us the magnitude, keep in mind. Now, if we want to look at, well, what's the direction? Well, we have to look at what's the charge. This is positive, so positive is going to go in this direction. This is negative, so negative is going to go in this direction. And so we say the field lines are oriented in the direction a positive particle would go. Now, electric field is a vector. And so we add vectors just like we would any other vector. We might have to break them into their components, use Pythag, use our trig functions and all that stuff. And so if we have electric field from 2 different sources, source A and source B, the electric field at point P is the vector sum of both of those electric fields, which gives us this resultant here. Notice the direction of these fields. A is going away from the positive charge. B is going away from the positive charge. So our result is in this direction. Let's look at an example here where we have an isolated point charge of 15 microcoulombs. And there's a test charge 20 centimeters to the right and has a charge of 0.8 microcoulombs. We want to determine what is the electric field at that point P where the test charge is. So we want to know, what is this electric field here? Well, this thing's experiencing a force to the right, which we can calculate using Coulomb's law. And that force is there because of an electric field. And we want to find that electric field. Now, since this is positive and that's a positive, both of these charges are positive, it's going to repel and go to the right. So we can find the magnitude of that force based on Coulomb's law to be 2.7 newtons. and then use this equation that we had from before to see that there must be an electric field of 3.4 times 10 to the 6th newtons per coulomb. Now, doing this, you should discover that, there's a little bit of redundancy in these two equations in that there's a Q naught here and a Q naught there, and since we're just going to take this divided by Q naught, we can simplify our equation for the electric field by saying that the electric field, the quantity, now keep in mind, this is the quantity, the magnitude, is equal to K times Q over R squared. Now we have to understand, what is this Q? This is the charge of our source. So that's the charge of the source creating the electric field, not the charge of the test charge that we're putting in. So this is a way that we can quantify what is the strength of the electric field outside of some charged particle or outside of some collection of charge. So if we have two charges, Q1 and Q2, both positive, and we want to know at this point P, what is the electric field? Well, we know that we're going to have an electric field to the right because of Q1, and we're going to have an electric field to the left because of Q2 because of the repulsion here. They're both positive. So we can find those two electric fields and subtract them based upon their quantities here, their distances, and this equation. And we can add those two vectors together, since they're in opposite directions, subtract them to find the resulting electric field. So we look at, well, we got to find the distance in that 3 meters separate the charges. We're at some distance d from Q1. So you do a little algebra here, say that the distance here is d squared, the distance here is 3 minus d, that quantity squared, and we put in the charges here for Q1 and Q2, and we solve for d to be 2 meters. Now, we need to interpret this answer. What does that 2 meters tell us? Well, in the original problem, we wanted to find the spot between the charges where the net electric field is 0. So like I said, to find the result, we have to add these two together, or, knowing that they're in opposite directions, we're going to subtract them. Well, if we want that result to equal 0, then that means their magnitudes have to be equal. So this D tells us that if we are 2 meters from this point here, Q1, then we have an electric field that cancels out with the electric field from Q2. So that is the point where we could put a charge theoretically and it would not move because it would balance between these two electric fields. Now let's look at a conceptual example here in that we have point charges that are fixed in the corners of a rectangle in two different ways. So we have A and B. Now in A we have positive, 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 and negative here, whereas in B we have negative, negative, positive, positive. And we want to look at which one creates a stronger field. Well, here we're going to have a field up and to the right because of charge 4 here, but we're going to have a field up and to the left by charge 3 and down and to the right by charge 1, and those two cancel out with each other because we're the same distance from corner 1 to corner 3. So our result is just going to be the field that we get from 4 and the field that we get from 2 added together. Whereas in part B, we have both of those fields here. This field right here is equivalent to that field there, and we have two of them. We have two of them that we're going to add together as vectors, and so this magnetic field, or excuse me, this electric field is a lot greater in part B. Electric fields dissipate as we get away from the source. However, we can create a condition where we have what we call a uniform electric field, and this happens in parallel plate capacitors. And so a parallel plate capacitor is basically we have this plate over here that is going to be connected to one end of a battery, and we're going to have this connected to the other end of a battery, and it stores up charge. We have positive charge stored up on this side, negative charge stored up on this side, so we get a magnetic field flowing through here. Now, as long as this space between these two plates is fairly small compared to the surface area, we get a uniform electric field inside here. And we can quantify that uniform electric field by taking the charge density, this is a lowercase sigma, divided by epsilon naught, which is just a constant, 8.85 times 10 to the negative 12th. Okay, and this actually, epsilon naught, is related to that k constant. K is equal to 1 over 4 pi epsilon naught. And so just a little unique relationship there. That's not dealing with anything we need to worry about right now. But we can find the electric field generated by a parallel plate capacitor using this equation, the charge density divided by epsilon naught. Now, electric fields, we can kind of depict these with electric field lines, and it's kind of hard because it's not something that we can picture intuitively, and so we draw these lines. So with a positive particle, we say that the electric field is going outward, away from it in all 3 dimensions. Okay, we only have 2 dimensions pictured here, but you can imagine all 3 dimensions. Now, we know that at some point here, the strength at this point A is weaker than at this point B. Now, one of the things to notice is the spacing between the field lines at B compared to at A. And so that's not just coincidental. When we have lines that are closer together, we say that the field strength is stronger. It's like a topographical map. If you've ever seen that, where you have lines close together, mean that the terrain is much steeper. Okay, and so same thing with electric field lines. When they're closer together, that means the field's stronger there. So the field is strongest when we're closest to the source. With a negative charge, the electric field lines looks the same, except notice the direction. The field is going toward the negative charge, which should make sense in that that's where a positive particle would want to go. It would want to go towards the negative charge, so that is the direction of the electric field. In a parallel plate capacitor, notice how I said it is almost uniform. It's pretty darn close to uniform, especially in the middle here. But we get these this little diffraction, little dispersion is what we call it here at the edges. We distort just a little bit in that it's not perfectly uniform at the edge. We actually get a little weaker when we get to the edge of parallel capacitors. If we have 2 charges next to each other, like a positive and a negative, their electric field lines will join, because we know a positive test charge right here would want to go towards the negative and away from the positive. Those are going to join together. So naturally, it's going to be stronger in the middle here than over here, because we're closer to both of these particles, wanting to pull us to the right and push us to the right based upon those charges. Conversely, if we had 2 charges of the same sign, those electric field lines would repel each other. So right here, naturally, we would expect there's a point where there's no electric field. We're getting a repulsion from the left charge and a repulsion from the right charge, such that they cancel each other out. And so the electric field directly in the middle is 0 when we have 2 charges of the same sign.